Oftentimes, you are presented with a scenario that has more than one outcome. What are the chances of these outcomes and how to quantify the amount associated with each of these outcomes? We are going to discuss how to approach this problem in the context of risk management using practical example and a case study. Before we begin, we need to agree on some terminologies. Uncertainty is the existence of more than one outcome for an event or an experiment. For example, when we flip a coin, this could be our event and the outcomes are either a head or tail. When we invest money, we either make a gain or loss. So in all of these events, the outcome is uncertain. When we try to measure uncertainty, we are actually interested in quantifying these outcomes in terms of probabilities, the frequency of occurrence, and their expected value impact. So for example, I want to be able to say there is a 20% chance of obtaining X. And by X here, I mean the variable of interest. In case of flipping a coin, this variable of interest could be the number of heads. If we are investing money, this variable could be the amount of gains that we are making. X, or the random variable, can take two forms, either discrete or continuous. Discrete numbers are the ones that can be counted, so the number of heads, for example, in the coin flips, or it could be a continuous, takes on an interval. The amount of money associated with investment can be an interval. It doesn't take an exact countable number, rather it takes a range of values. Another example of a continuous variable is the height of a person, the weight of a person, and all these can take a range of numbers. So whenever you find yourself counting, this is a discrete variable, and when you include a possible range, this is a continuous variable. When studying random variables, we are actually interested in their distribution, and distributions depicts the way they behave across the range of values that they could possibly take. And as we said that uncertainty is associated with several outcomes. When these outcomes are unfavorable, they are denoted as risk. So for example, when we invest money, one of the possible outcomes that we lose this money, so there is risk associated with investing money. The nature or the description of the outcome is closely tied to the impact it has, whether it is actually a gain or loss. Our case study will be measuring the risk of leasing an equipment. This is actually a real case study that I have encountered in the past. So to put all this into practice, let's simulate flipping a coin 10 times and counting the number of heads. We are going to repeat this process, which is flipping a coin 10 times, for 500 times. So our experiment or event is flipping a coin 10 times, and our random variable, X, is the number of heads in these flips. And we are just basically going to repeat it for 500 times and observe the range of values that the number of heads can take, or the random variable, which is X, can take along these experiments. We can study this behavior using a histogram, and histogram, as we see here, depicts the possible ranges of the random variable, which is the number of heads, and their actual counts. So for example, in this experiment, 2 appeared 20 times, 5 appeared almost 150 times, 4 appeared 100 times, and so on. So we can see here that the most frequent number of heads that we can observe in this experiment is 5. So now we know what is a distribution, what is a histogram, and how to depict a distribution in histogram, what is a random variable, and we are ready to apply these concepts to a data set. If we consider the experiment we have done earlier, that we collected a bunch of samples and we defined a variable which is being the number of heads as X. We can actually think of this as any data set that we work with, which includes a bunch of samples about a phenomena that we want to study. Our data set here is the insurance data set, which include a bunch of samples about patients of a particular insurance company, along with their demographic characteristic and insurance expense. The aim of this data set is to be able to predict the insurance premium that this company charges to each customer based on their expected or predicted expense. In that sense, we can actually define our random variables to be age, gender, BMI, children, and so on. And we can see that each of these variables take on different forms. For example, age has numeric values, gender has categorical, a BMI numeric, and as we know, we can distinguish between numeric as being either discrete or continuous. For example, in this case, we can consider BMI as continuous, because it takes a range of possible values, while children has a fixed countable values. Similarly, we can consider age to be continuous, but you can actually argue that it takes a fixed countable values like 19, 18, but this is actually not the case because it can be expressed in years and months. We are not bound by the actual values that each variable take. For example, we can switch between numeric and categorical as we wish. For example, smoker here, it has two values, yes or no. We can denote these as discrete variables using 0 and 1 as in children. So for example, I say that whenever a person is a smoker, I'll denote this to be 1, and if it's not smoker, it will be 0. So I have changed a categorical value into a discrete representation. Okay, so one thing we can do to understand the distribution or to understand the behavior of this random variable is to plot their histograms. Here are the histogram of the numeric features. We can see that each of them take a different shape. If we look at age, it's almost exactly equal along the range of the values except for this bar here. And for BMI, it is looking like a curve that has peak around 30 and then decreases on both sides. For children, it shows the number or the frequency when patient has 0 children, 1 children, 2 children. And charges also looks like BMI but with a tail towards the positive values. Each of these shapes actually has a name and a type of distribution. When you start working with distribution, you will actually be familiar with these shapes and types as you see them. For age, we say that it is uniformly distributed because we see here that each range of possible values has equal chance of being represented. For BMI, it is normally distributed where it peaks around 30 and decreases on both sides. For children, it's discrete because we see here that it takes countable fixed values and each value is represented by their frequency of occurrence. Charges is log normally distributed. It means that most observations have lower values and only few observations take some large values. What we are actually interested here is the y-axis of each distribution. We here see that this is a count and this count represents the range of each bin. A histogram bins the ranges of the observations and count the number of observation in each bin. So for example, from age 0 to 20, there is 200 observation. From 20 to 25, there is 100 observation and so on. We can change this y-axis to display probabilities. For example, if we come here, don't worry about the code because we are going to discuss the code that generated this notebook at the very end of this session. So if we change state to be probability, the y-axis changes to reflect the probability distribution of these values. Probability distribution actually differs from one shape of a histogram to another. You can see for children, it's between 0 and 0.4, but it's much less in BMI and age. As you recall, age and BMI are continuous variables and children is a discrete variable. And the reason for the change or the difference between the y-axis is actually the way probabilities are calculated. Each distribution has a specific way of calculating these probabilities because they denote different things. For example, for BMI, it's continuous distribution. The probabilities along the y-axis tell us something about the interval around a given value. So 0.1 is not the probability of observing 30. It's actually the interval around 30. While in a discrete value, the probabilities actually depict the height of each bar. So for example, patients with 0 children represents 40% of the samples in the dataset, and patient with 1 children represent like 25% of the sample and so on. So what's important to note here is that probabilities for continuous variable is concerned with intervals around a fixed number or a given number. We can denote this actually by changing the probability to be density. So we see that it's slightly changed here, and now we can be comfortable that for continuous variables, the densities actually reflect the interval around a given value, but for discrete, it doesn't make much sense. Actually, you can see here that it's exceeding actually 1. So how can we calculate, or how are y-axis calculated, whether it is a density function or a probability function? Each of these has actually its own formula, and we are going to discuss this next. But first, let's look at some of the summary statistics of these variables. If we look at age, for example, it has a mean of 39.2, standard deviation of 14. Standard deviation is the dispersion of values around this mean, the minimum value, the maximum value, and the percentiles. Percentiles basically tell us that, for example, for age, 75th percentile means that 75% of the data lies below 51 of age. It's important to note that each of the distributions that we have discussed earlier has its own parameters. If you want to describe a distribution in terms of probabilities, we need to know their parameters and pass them to the probability function to get their probabilities. So continuous random variables can be represented using normal distributions. To get the probabilities for a random variable that is normally distributed, we use probability density function. Probability density function takes two parameters, the mean and sigma, and calculates probabilities of intervals around this curve. So if you recall, we said that from the histogram, we said that the values of the BMI takes a bell-shaped curve, and we were wondering how the probabilities were actually calculated. This is how it's calculated. The parameters are passed to the PDF function, and the PDF function spits out the probability that a given X value lies within a specific interval. The normal distribution is centered around the mean, and the mean here is 30.6, which is this black line. The key takeaway here is that the probabilities of continuous variables that follow a normal distribution can be estimated using probability density function using the parameters from the dataset, which is the mean and standard deviation. And the probabilities depict interval beneath this curve. If we look at the plot on the right, it is a distribution for the same variable, the BMI, but in terms of z-scores. And z-scores are basically a normalization of the values of BMI. We subtract from each value 0 and divide by standard deviation. And this is just to depict the distribution in terms of distance from the mean rather than interval or a range of specific values. How is this useful? If we wish to compare two distributions together, we can compare their z distribution together rather than looking at their specific values. One property of normal distribution is the empirical rule, which states that 68% of the data lies within these orange lines, 95% of the data lies within these red lines, and 99.7% of the data lies within these green lines. This means that if we have a data point that is outside the green lines, we can consider this to be outlier. And the reason why that this green line here is far away from the distribution is because in this dataset, there are no values that are less than 3 standard deviation away from the mean. And you can actually see this here in this tail towards the positive, long tail towards the positive values. If you are wondering where did we come up with these values of empirical rule, we can use what is known as Gaussian error function. And Gaussian error function evaluates the probability that a random value lies within a given interval. So just to not be bombarded with functions, the main functions that we are using is the probability density function to estimate the y values, and the empirical law tell you something about the distribution of values within the curve. The area under the curve is 1, and the cumulative sum of the y-axis is equal to 1, because we said that each part of this represents an interval, small interval under this curve. The cumulative sum must equal to 1 because the area under the curve equals 1. We can actually do the same for discrete values. For example, smoker. If we want to find the probability when choosing one patient randomly, whether it is gonna be a smoker or not, we can use probability mass functions. And probability mass function, just like probability density function, tells you the probability of a given value of a random variable, and it takes a parameter of p, which is the probability of success, and success can be defined the way you want. So, for example, in case of a smoker, I'll say that the probability of success is that a customer is actually a smoker. So we pass on the probability of success to the probability mass function, and it spits out the probability distribution of the values within the random value. So these are actually the probabilities obtained from the dataset, and they are basically the number of smokers divided by the total number of patients. And these are the probabilities that are obtained from the probability mass function. And this is the way the distribution looks like. There are way more non-smokers than smokers. What's important to note here is the y-axis. The y-axis depicts the mass of each bar rather than the interval around a given number in the probability density function. So in probability mass function, we are interested in looking at the heights to know the probability of a given value in the random variable, while in probability density function, we look at intervals. This is really important to distinguish between. When we find the probability distribution of specific value using probability mass function of a single sample, it's called Bernoulli distribution. Now, what if we actually increase the number of samples to include several other customers? In that way, it's gonna be a binomial distribution, and binomial distribution is a specific case of a Bernoulli distribution where the discrete value has only two outcomes, either smoker or non-smoker, but actually the number of samples is much larger than one. Earlier, we used PMF to find the probability of exactly one smoker in a randomly selected sample. Now we use a binomial distribution to find the probability of smoker in n samples. So the parameters of the distribution here is n and p, where n is the number of trials and p is the probability of success. And we said that success is what we actually define. And for the case of smoker, we said that the probability of success is that a patient is actually a smoker. So in 25 patients, and with probability of 20% smoker, as we saw earlier, we expect that the probability mass function for observing 5 patients is 19.6 or almost 20. Now, if we change 5 to be 9, for example, we see that the probability decrease, and it actually makes sense because there is only 20% chance of observing a smoker, and as with the number increase, the probability gets smaller and smaller. Notice that we are here fixing the parameters, which is n and p, and changing the value that a random variable can take. And this depicts the probability of observing this random variable. What if we fixed, let me get back to 5. What if we fixed the data, like we fixed the number of trials and we fix the number of patients that we expect to see, and changed the probabilities? This is no longer a probability, rather a likelihood. Likelihood of observing the probability of 40 for 5 patients out of 25. So this might sound confusing. Let's recap. When we fix the data and change one of the parameters, we are actually looking at the likelihood of obtaining this parameter. And how likelihood differs from probabilities, we will see next. So another variation of discrete distribution is multinomial distribution, and this is actually where the number of outcomes is more than 2. So if we recall, children had several outcomes. The patient either has 0 children, 1 children, 2 children, and so on. So if we want to model this phenomena, we use multinomial distribution. It's basically the same, but we need to account for the probability of observing each of these outcomes. First, let's look at the distribution or the probabilities from the dataset for each value of children. For example, 0 has the highest probability of occurrence, 1 is 24%, and so on. And if we want to use this to model observing exactly n number of children in a given sample, we use multinomial distribution. So the parameters stay the same, n and p, but this time p takes a range of value for each of the outcomes. So for example, here we have this is 24 total samples, and we are trying to find the probability of observing exactly 1 patient with 0 children, 2 patients with 1 children, 3 patients with 2 children, and so on. So what would be the probability of observing in a total of 24 samples, observing exactly this number of patients with the corresponding children values? It would be this very small probability value. And it actually makes sense because if you look at the bulk of the values are concentrated where the variable is less likely to happen. If we remove these from our sample, we see that actually probability is increasing. It's not increasing by much, but it's higher than what has been previously displayed. And let's rerun this because I want to... Yeah, this number is actually very small. This negative 20 means that you put 20 zeros before 4. So it is 20 zeros, then 4. Now when we close this, it's actually 3 zeros before the number starts to happen. So this is actually higher than the earlier one. And if we close this one also, by closing, it means that we are reducing the number of samples to be observed from the less frequently occurring ones and expecting to see more of the ones that has higher chance of occurrence. And we see that the probability is actually increasing. If we increase one, the first, dear children, the probability is actually increasing. Now it is 4.01% rather than being a very small number. So in a nutshell, we can summarize this section by knowing that each variable in a dataset can be considered a random variable that can be modeled using a specific distribution, and each distribution has a specific parameters that is used to produce the probability of observing these values within this variable. And how would this actually even be helpful? We will see next. Before we close the subject of probability functions, there is one really interesting function to discuss, which is the cumulative distribution function. If you recall, when we talked about a normal distribution, we said that the y-axis represents the probabilities of interval within beneath this curve, and the cumulative sum of the probabilities amounts to 1 because the area under the curve amounts to 1. We can actually use another function known as cumulative distribution function to model directly the probability of observing a value less than or equal x. So, for example, when we pass the parameters of BMI, which is the mean and sigma, to the cumulative distribution function, we get this curve. This is known as sigmoid curve. The first immediate noticeable thing is that it ranges between 0 and 1, which gives us directly the probabilities of observing each value around the curve. So for example, if we go to 50% chance, which is 0.5, and move along the curve, then find where it lands in the x ranges, we'll see that it is around 30.4, which coincidentally is the median of the distribution. These are the summary statistics that we have displayed earlier, and these are the percentiles. And we said that the 75th percentile means that data lies below 34%, and 50th percentile data lies below 34%, and so on. So we can think of CDF as a quantile function that tells you the probability of observing a value less than or equal x. And x is the range of values that a random variable can take. So for example, the probability of observing a value below or equal to 30 is 50%. And if we go to 70, we will find that it is 30. So what is really useful about CDF is that we can eyeball the probabilities directly from the y-axis. Let's get back to our important question. How can all this be useful? Well, if we want to model a distribution or model a variable, a specific variable, knowing something about the properties of its distribution, we can actually generate numbers that follows or respects its original distribution. For example, if I want to pick randomly from a BMI variable, instead of going blindly and picking any number, I can use the previously stated functions to pick a number that has similar characteristics of the original ones that's found in the BMI. And by characteristics, I mean the probability of occurrence and the range. So if BMI ranges between, for example, 0 and 50, I don't want to be picking 60 because 60 doesn't fit into the distribution. And if it ranges between 0 and 50 and it peaks at 30, I don't want to select many samples from 40s and less sample around 30, and so on. Here we have selected just one random variable from the distribution, and if we repeat this many times, we actually get a distribution of values, randomly selected values that follows the original distribution. The plot on the left is the random variables that we have generated, and on the plot on the right is the actual values of the BMI variable. So this is actually very powerful when it comes to running simulations. But before we turn to our real case study, we can also do this for discrete variable. When we sample randomly from a discrete variable, we expect to see that the randomly sampled variables are actually respecting the original distribution of the variable. Okay? Now into our case study. This is actually an interesting and very dear case study to my heart. It's about finance lease or leasing in general. We were actually trying to assess the risk associated with leasing an equipment for one of the clients in terms of impact and likelihood. And this can actually take many forms. You can review the lease contracts and you can find some terms and conditions that are not favorable to the company. You can assess the interest rate implicit in the lease and compare it to the common or the prevailing interest rate in the market and see whether this is actually reasonable or not. But for the sake of this demonstration, we are gonna focus on assessing the feasibility of the lease, whether the expected returns of this equipment is gonna actually justify the cost that is being associated with this investment. So to begin with, we will discuss 3 different scenarios to approach this problem. And this problem is actually framed in the context of risk management. Risk management is all about identifying risks, then trying to deal with it in some sort of a way. And in my opinion, the most critical part of this process is to identify risk in the first place. Because if you can identify risk, you can actually measure it and deal with it. But if you go blindly and didn't identify risk, you can think that you are actually doing okay while you are actually not doing okay. So usually we start an exercise like this by comparing alternatives. For this particular scenario, we can either go directly and purchase equipment. The associated cost with a direct purchase is 441k. We can either make an installment purchase, which like similar to a finance lease but different financing arrangement, and this is again the associated cost with installment purchase, and this is the finance lease that was actually undertaken by our clients. Of course, when you think of lease, you won't think of direct purchase because you actually might not have the enough finance arrangement to go directly and spend this money all at once. But it's important to have a look at the direct purchase total cost and compare it to the whatever alternative you are going to pursue, because it is going to tell you something about the finance charges or the finance cost that you are actually incurring. So my first approach was to quantify the amount of direct purchase and the amount of another alternative, which is installment purchase. Installment purchase differs from finance lease in terms of financing arrangement and some terms and conditions, but in this particular case, it was very closely related, and the client can handle actually both finance arrangement of the installment purchase and the finance lease. So it will come down to comparing the total cost of each alternative. The first thing to note is that finance lease is actually way higher than installment purchase. This can tell you something about the interest rate used in calculating this lease, because when you lease an equipment, the lessor or the person who is leasing you the equipment or giving you the equipment must earn some money. He quantifies this money in terms of interest and charges you these interest across the payments that are going to happen in the term of the lease. And the term of the lease in this case is actually 4 years. So one thing to note and to assess, why is the finance charge in the finance lease actually higher than a similar alternative that is actually available? This is one approach. Another thing is that you can actually make a discounted cash flow analysis, calculating the present values of future payments. So if you are gonna make a finance lease payment along a 4-year period, you wanna know the real value or the present value of these actual costs now, today. And if you are expecting some returns that is related to this particular lease, you want also to know how much the present value of these returns today, so you can actually compare between them. Normally, when the associated cash flows is higher than the cost of the lease or the cost of the investment, it indicates that it's okay to pursue this alternative. But if the cost is actually higher than the expected cash flows, it means that it's actually not a good investment. So this is the present value of the cash flows, and this is the present value of the lease, and the net present value of the lease is positive, so it seems feasible that this leased equipment is actually something worth getting. And similarly, of course, for installment purchase, because it's actually lower, so it's going to be lower than the cash flow, the present value also is positive. But notice the difference between the present value of the installment and the lease is much higher, and this comes from the fact that total cost is actually higher in the lease than the installment purchase. Okay, so these are actually all good, but these figures are calculated using averages across the lease terms, and the input to the cash flow usually is not an exact number, rather a range of values. If the cash flow consists of several components. Each component can have a specific range of values that takes. For example, if we compare it to BMI has a range of values across each patient. Similarly, the cash flow has a range of values across the terms of the lease. One way to address this is by performing simulation, and when we perform a simulation, we want to sample from these ranges and make a calculation for each sample. What we are actually trying to do with a simulation is that we are trying to calculate several cash flows across the lease term, giving the ranges of each component, and then compare each cash flow to the equipment lease and see what are the probabilities that the equipment lease will actually exceed some of these cash flows. So how to calculate these specific figures or the specific cash flow from this range of component of cash flow? Using the knowledge that we know so far, we can establish a distribution for each component, then use the parameter of this distribution to sample random values from them, and use these random values to calculate the cash flow and then compare the cash flow to the actual installment cost. The challenge here is, of course, to model it with the proper distribution. This is one thing. And then to get the parameter of distribution. If you have data, previous data or historical data, you can do this easily, or you can actually get it from a subject matter expert, for example. We will consider that the cash flow consists of 3 components, A, B, and C, and each component has an upper and lower bound. Upper and lower bound means that with a specific confidence level, we are sure that the true value lies within these ranges. So if these ranges represent 90% confidence interval, it means that component A, there is a 90% chance that the true value of A lies between 2 and 1. Similarly for B and C. Okay? To run a simulation, we just establish a distribution and we consider that each component is normally distributed. Use the confidence interval to calculate the distribution parameter. Sample from the distribution and then get this nice ranges of values for each component. Then we simply compute the actual ranges of each component and multiply by the number of units to get the expected cash flow to compare the cost of the equipment against. Now it's time to look at the probability of loss, which is when the discounted cash flow, if you want to compare cash flow directly, is less than the lease. We'll use histograms to plot this. On the x-axis, we have all the discounted cash flows, and on the y-axis, we have the accounts of the occurrence of each of these cash flows. The red line represents the value of the lease. So for lease, we can say that there is an 18% chance of losing money because this area here amounts to 18%, where the cash flows will actually be less than the cost of the lease. And for installment purchase, the loss is much less. It's 6% only because this area here amounts to 6%, where the discounted cash flows will be less than the cost of installment purchases. How did we come up with these percentages? By using the cumulative distribution function. We can even make these histograms come to life by using another plotting module, which makes the histogram interactive. You can actually select each area of the bar and get the range of the bar and the associated cumulative distribution. So if we want to summarize this exercise, if we actually started this exercise considering only the lease, we would have thought that it is the best alternative to pursue. But when we added the other option of installment purchase and when we did this simulation, we actually were able to quantify the amount of loss associated with each and actually to question some of the arrangement or the terms and condition of the lease, being, for example, the finance cost charges to our client. Hopefully by this you have a better understanding of distributions and how you can apply distributions to real examples. What's coming next is that we are gonna discuss the mathematics behind all what we have been doing so far and also discuss the code used to generate this notebook. Okay, let's start with sampling from the distribution, because this is still fresh in our mind and this is what have been discussed earlier. There are several ways to sample from a distribution, and one of them is to use the inversion method. Inversion method is actually using the cumulative distribution function to come up with x values. This equation here is the equation of the cumulative distribution function. It uses Gaussian error function that we have discussed earlier or noted earlier to find probabilities of each value of x. Now, if we inverse this equation, we can actually get X values using the associated probabilities. One challenge would be how to find the associated probability to use in this equation. If we look at the cumulative distribution function of BMI, and specifically if we look at the y-axis, we find that it ranges between 0 and 1. If we go and plot the distribution of these values, we'll find that it is uniformly distributed. So this means that if we can actually generate probabilities that are uniformly distributed, we can plug them into a cumulative distribution function with the parameter of the variable of interest, which is, for example, BMI, and it will give us the associated values of X. It is similar to going along this y-axis and pinpointing a probability of interest, then going to seeing where it hits the cumulative distribution function and finding the corresponding value of X. And when we did this for BMI, we actually got a distribution of values that resembles the original distribution. On the left, these are the original values of the BMI, and on the right, these are the values that are randomly sampled using the inversion method and the inverse of CDF. If we want to learn more about the probability density function and probability mass functions, for example, if we start by continuous random variables, if a random variable follows uniform distribution of parameter A and B, where A is the lower limit and B is the upper limit, the PDF can be expressed as 1 over B minus A. This is, of course, if X belong to A and B. And this makes sense because if you are trying to model a random variable that is bound between 5 and 10, for example, you won't expect to see the value of 12 or 13 because it is outside the range of the boundaries of the random variable. So F is the PDF, the representation of the function of the PDF, and F of X given A and B is 1 over B minus A, otherwise it is 0. Similarly, if the continuous random variable follows a normal distribution with parameter mu and sigma, we can model it using this equation, and this equation actually has two parts. This part over here is a positioning part, if you might say, and this is actually a scaling part. We are subtracting each value from the mean and dividing by standard deviation, similar to what we did in normalizing and finding the z-scores. And this actually controls the position of the curve, either left or right to the mean, and the thickness of the curve. Now, when it comes to finding the area, the total area, or positioning or scaling the total area to fit into this distribution, we use this part here. Similarly, if we consider discrete random variables for a Bernoulli distribution, which represent a single observation or a single trial with parameter P. P is the probability of success. The PMF is P to the power of K multiplied 1 minus P to the power of 5 minus K. If K belongs to 0 and 1. Of course, it is 0 and 1 because if you take this as an example of smoker, it's either 1 if it's smoker, 0 it's not smoker. If we model a smoker variable, we say here that PMF of 1, 0.2 to the power of 1 multiplied by 1 minus 0.2 to the power of 0. Here will be 0.8 to the power of 0, which is 1. It will give you 0.2. The PMF of 0 would be equal to 0.2 to the power of 0. And anything to the power of 0 gives 1, so 0.2 to the power of 0 is evaluates to 1, multiplied by 1 minus P, which is 0.8, because P is 0.2, the probability of success, and 1 minus P is 0.8, 0.8 to the power of 1, which is actually 0.8, so it is 0.8 multiplied by 1, which is 0.8, which is actually the probability of non-smoker. Now, if we have a binomial distribution, it is actually the similar case. However, this term here is added, which is the binomial coefficient, and it reads n choose k, and it just models the different ways we can obtain the desired outcome in a specific experiment. When you expand this, it is actually n factorial divided by k factorial. And factorial means that we multiply a number by its preceding numbers till we reach 1. So, for example, factorial of 5 is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. And this term here just tells you how many ways you can actually obtain the desired outcome from the experiment that you are doing. So, as a way of example, if we flip a coin 3 times and then we want to know what is the probability of observing 2 heads, this is actually a binomial distribution because we have n number of times that we are going to run this experiment for. So the binomial coefficient will read like this: 3 choose 2. When evaluated, it gives 3. which means there are 3 ways to obtain exactly 2 heads. And if we simulate or write down the sample space, which is the outcome of our experiment, tossing a coin 3 times, we'll find that we have a total of 8 outcomes, and there are actually exactly 3 times that we obtained 2 heads. H represents heads, T represents tails, and in the first toss we have head, for example, and the second toss is head, and the third toss is head. This is one possible output. Another possible output is that the first toss is head, the second toss is head, the third toss is tail, and so on for the rest. So 3 choose 2, which is n choose k here in the coefficient, is the number of ways we can obtain exactly 2 heads in a total of 3 tosses, which has a sample space, and the sample space denotes the total possible outcome of this experiment of 8. Similarly, we can directly calculate the probability of observing exactly 2 heads by dividing the number of desired output to the number of total output, which is k over n. Okay? Before we expand on this, because this is actually really interesting and you will find that it is so intuitive when we discuss it later. Let's finish with this. Multinomial distribution is actually a expansion of the binomial distribution where we include the probabilities of each outcome as we saw in children example. Now, of course, when you use Python, and this is the beauty about Python is that it has a lot of modules that make implementation of these functions that we saw earlier so easy, but it doesn't hurt to actually code them yourself to know how they actually work and to get an understanding of what's happening under the hood. So I here coded each of these mathematical functions, and we will be using them in the coming demonstration. But you can actually either code them yourself or use the modules available as we have been doing up to this point. Now, probability versus likelihood. If you recall, when we were discussing the number of smokers, and we said that when we fixed the parameters and changed the expected values of the random variable, we were actually looking at probabilities. But when we fixed the data, which is the number of values and the n samples, and we changed probability, we are actually looking at likelihoods. So now let's get back to our probability of outcome in 3 tosses. We ran an experiment of tossing a coin 3 times and observing the number of exactly 2 heads. And we calculated the probability directly by dividing the expected outcomes over the total outcomes, which is 0.375. We will be demonstrating it using a binomial distribution. So we are going to flip a coin 3 times and record the number of values that we would expect to see given a fixed probability. So our coin is a fair coin, so it has a 0.5 chance of landing on either head or tail. We will pass to our function n equals 3 and p equal 0.5, and we will evaluate this function along a range of k values. We can see here that obtaining exactly 1 head is similar to obtaining exactly 2 heads, which can be confirmed by our sample space here. These are the outcomes where we can expect to see 2 heads. Similarly, we can here expect to see 1 head 3 times of 8 times. And there is very low chance of observing 3 heads, which is actually happened 1 time here, which is 1 over 8, which is very low. Okay? So this plot shows the probability on y-axis of observing x values in this distribution or in this experiment. And this is what we have been doing actually up to this point. Now, if we changed the scenario a bit and fixed the data, so k is fixed, which is the number that we wish to observe, which is 2, and n is fixed, which is the number of trials. Our question here, what is the probability that maximize seeing this scenario? So we will use the same functions that we have been discussing, but instead of fixing the parameters, which were n and p, we will fix the output and keep it changing p. So we are actually interested in the highest probabilities that we can get of observing 2 heads in 3 tosses. The x-axis are the probabilities that keep changing, and the y-axis refers to the likelihood of observing these probabilities. It peaks at 0.7. What actually does this tell us? It tells us do not expect to maximize the chances or the probability of observing this scenario using a fair coin. Why? Because the fair coin has a fixed probability of 0.5, and the maximum probability of this scenario is actually 0.7. 0.7 actually makes sense because if you expect to see 2 heads in 3 tosses, when you just divide 2 by 3, it gives you 0.7. So this is known as maximum likelihood estimation, which is finding P that maximizes the scenario. And how is this helpful? It depends on how are you seeing the data. If you have a data and you are actually interested in knowing the probability, this is what we have been doing so far. You can actually calculate the probability from the data directly. And rest assured that the probability that you have calculated is the maximum probability that you can get given these data. Simply put, as we know the coin is fair, it has 0.5 probability of observing either head or tail. We can't maximize the chances of observing 2 heads and 3 tails using this fair coin. Simply put, we can actually apply this to our dataset. If we fix P and N, which is the parameter of the distribution, and find the probability of observing K smokers, we will get this distribution which peaks at 5, and the actual probability that we can expect, or the maximum probability, is 0.2, which makes sense because we know that the probability of smoker is 0.2. Similarly, if we switched the scenario, fixed K, which is the number of smoker, and N, and change it P, we will find that the peak of the distribution is at 0.2, which means that the maximum likelihood estimate for this scenario is 0.2. If we were presented with a scenario that we actually obtained 8 smoker in 25, we can no longer expect to see it peaks at 0.2. It will have this shape, and this shape tells us that the peak of the distribution is at 0.3. And this tells us something about the scenario we are dealing with, which is it's not likely that 8 customers in 25 actually belong to our original insurance dataset, because we know that the probability of smokers in our dataset is 0.2. So this shift in distribution between our dataset and the scenario we are dealing with here, the 8 from 25, means that this scenario is not likely to have come from our insurance dataset. I hope that it makes sense. If you have been noticing, a really interesting thing is that the peak of each distribution, either here or earlier, is exactly at K over N. K being the number of smoker we expect to see, and N is the total number of samples or trials. So the maximum likelihood estimate for P is actually K over N. It might sound like a naive thing, but actually there is a mathematical notion behind it. If you want to calculate an exact figure from a given distribution, we find the derivative of the line that is tangent to the exact point that we are interested in. So for example, this tangent line over here is exactly at the peak of the distribution, and if we find the derivative, the slope of this line, we can actually find the corresponding point on the x-axis. This is for discrete distribution, and for continuous distribution it is actually similar, but in continuous distribution we have 2 parameters, mu and sigma, so we need to differentiate the probability density function for each value of x using these 2 parameters. So instead of using the normal probability density function, we use the log probability density function because it makes calculations easier. And we can see here that if we start with a random guess of each mu and sigma, this is the value of probability density function at this point. And if we keep differentiating the equation, differentiating means we are changing actually the values of mu and sigma and calculating the function. We are seeking to maximize the log likelihood, and maximizing, this is a negative function, so decreasing means that we are actually maximizing the output. We will see that it maximizes at mu 30 and sigma 6, which is actually the mu and sigma of the dataset. So similarly, the maximum likelihood estimate of the parameters of a Gaussian distribution is those of the actual dataset. I hope you guys find this useful. Now let's go quickly through the code. Let's start by this function. We first start with an initial guess of the parameters. Then we pass this guess to our log likelihood function. And in our log likelihood function, we are using SciPy. This is a module where we establish a distribution with mu and sigma. And we pass the associated x, and x here is the random values of BMI. And we are actually summing this equation because the maximum likelihood estimate for a normal for Gaussian distribution is the maximum likelihood estimate of each value of x. So you need to sum these likelihood together. And because we are using log likelihood, we are actually summing. If we are using the PDF, we would have been multiplying it. And the minus sign here indicates that we are maximizing this function because this function is going to get into another module, which is minimize. And this is where actually the calculation of the derivative happens, where we try different values of our initial guess parameter with this function and find the best parameters that maximize this equation. So here we are passing our function to minimize, then our initial guess, then we are printing what is actually happening at each iteration. If we look at the code for finding the likelihood of different values of p, we calculate the PMF using the binomial function, passing n and p, and evaluate it at each value of k, and k here is fixed. And n is fixed, k is at 8 and n is at 25, and p, we are changing p across different ranges of values. Then we are plotting and printing the results. Okay, similarly, this is the same thing we are been doing here for the example of 5 over 25, the same thing, calling the binomial, fixing 5 and 25 and changing p's, and we are plotting p's at the x-axis and the probability mass function or the likelihoods at the y-axis. This one is similar also, and when it comes to sampling from a distribution, we actually first indicate the number of samples we wish to generate. And in our example here, we used the total number of samples in the data frame. And to get the total number of samples, when we call shape, it gives you the number of rows and the number of columns. You select the number of rows by accessing the first portion of the result shape. Now you calculate P, and we said that P will be generated using uniform distribution. So P uniform, and uniform, you know that there must be an upper and lower bound. It will be between 0 and 1. And the number of samples that we want to generate is this that we have identified earlier. Now calculate the inverse CDF using the functions we discussed earlier. Here the inverse of a Gaussian error function is actually coming from a module. We are passing to it the p's that we are generated, and we are plotting the result. The x-axis has the generated variable. We are using KDEs. KDE estimates directly the probability density function of each variable. So we are using KDE on original samples and another KDE on the generated sample from the inverse distribution. Okay, this is actually also the same. When we sample, here when we wanted to prove that the y-axis is actually uniformly distributed, we calculated P using the cumulative distribution function evaluated at each value of x, establishing a normal distribution, passing to it the parameter of the distribution, and evaluating it at each value of x. So we get the p's, then we plot the p's and see their distribution along the y-axis, and we see that it is uniformly distributed. Plotly is actually pretty straightforward, but the actual trick here was to compute the CDF along the bins. We want to calculate CDF at the exact bin ranges that Plotly plots. We first instantiated a bin range from the minimum and maximum results of the discounted cash flow. Then we used NumPy to plot a histogram and get the count and bins, and we evaluated the cumulative distribution function, passing the parameter of the distribution at each value of bin, then pass this all into a histogram function of Plotly, where axis is the DCF and number of bins is the length of bins that we have calculated here. And these are actually some decorative stuff to remove the background, make it white, and remove the x-axis and make colors black and red like this. The most important thing is actually to know how to fit a distribution, then to sample from it. And this can be shown here in our Monte Carlo simulation. First, let's see how do we fit a distribution to a data. We call the module, which is SciPy. Then we specify the distribution, and we pass the mean and standard deviation of this distribution. Okay. So by this, comp A represents a normal distribution with mean, M, and sigma. Now, when it comes to sampling from this distribution, you just call comp A and random variables, and you specify the number of variables that you wish to extract. Random state fixes the randomness in the operation so that every time you and I run this example, we get the same exact results. Now, when it comes to the simulation, actually, we said that each component of the cash flow consists of an upper and lower bound. And because this is a confidence interval, not actual mean and sigma, we used this interval to calculate the mean and sigma. So to calculate the mean, we just add the upper and lower bound divided by 2. And to calculate sigma, we subtract upper from lower bound and divide by 3.29. What is 3.29? 3.29 is the width of corresponding confidence interval. So if we say that we are 90% sure that something is within a confidence interval, to calculate the width of this interval, we divide by 3.2. And 3.2 is actually the distance from the mean at both sides. So if we look at the z-scores, let's, for example, say that the red ones are 90% confidence interval. So this space here from 0 to 2, for example, it's 1.6, and from 0 to negative 2 is 1.6. So if you are 90% confidence, so you are sure that it is between these amounts, and you add these amounts together to find the width of this interval. So this is basically it. You fit a distribution, sample from it, then create a data frame from the results. When calculating the net present value, it's actually straightforward. Find the amount of annual payment of a lease by dividing the lease over a lease term, which is 4. Then we just multiply the annual lease payment by discounting factor. We just multiply by 1 divided by 1.1 to the power of n. Then finally we compare the present value of cash flow to the present value of the lease or the installment purchase to get the results. This is actually called a list comprehension, where you repeatedly do a function several times. So this is the Monte Carlo simulation. I think this is the most important part of this demonstration. Sampling from discrete random variable. This is actually also the same. This time we did it differently. RV discrete, similar to the binomial distribution, where you fit the counts and probability of each value. Here, because we are using a multinomial distribution for the number of children, we are fitting the counts and the associated probabilities. Then we are sampling from the fitted distribution. Cumulative distribution. Cumulative distribution, you can see how we calculated the CDF. If you recall, we said that CDF, the y-axis, is a cumulative sum of the probabilities. We use the histogram, NumPy histogram on BMI to calculate the probabilities and the number of bins. Then we just called CumSum, which is this, to cumulatively sum the probabilities generated by the histogram. And of course, these probabilities are generated using the probability density function, because you see here density is true. And the number of bins, it's weird, that's 37. That's because you want the cumulative sum to equal 1. So you just try several times here until you reach the sum which is equal to 1. And then you plot it using the bins, which will refer to the x value and the cumulative sum of the probabilities. Okay. This thing here is called a widget, which takes a function and make you interact with it by changing some of the variables. So if you look at the code, we first establish our multinomial function of modeling children distribution. So we actually want to interact with this function by changing the number of k. K is represented by these parameters, and these parameters are actually a range of values, and this range of values takes on a minimum and a maximum. You run the cell, you want this value to be at 1. So if we run the cell again, you see that it starts at 1. It could have started at 3 or could have started at 10, but if you want it to start at 1, then 2 and 3, then you will be able to adjust it accordingly. Interact is a module where you pass it to the function and the parameters that interact with this function, which you have already been established or defined earlier in the function you have passed to it. Okay? It's really nice to have a widget to interact with the function instead of having to manually recalculate the function several times. And note that when you actually change the values here, the cell rerun itself automatically. If you watch this circle here, when it flashes, it means that Python is actually running in the background. So you see that every time I change, the cell is actually being rerun and it is displayed here. Similarly, this is the interactive widget. I think this pretty much covers it. Maybe we can see how we calculated the z-scores. The one on the right, the PDF, using the real values of the variable, BMI, and this is the associated z-scores. And how did we calculate these scores? Simply by subtracting mu from each value of x and dividing by sigma, which is the standard deviation. And again, we are calling a normal distribution, passing the parameters, and then evaluating on each value of x to calculate the probability density function. And we are plotting x values, which is the BMI values, at the x-axis, and the associated probability density function at the y-axis. We are using 0 and 1 as parameter of the distribution because the normalized distribution or the standardized distribution has a mean 0 and a standard deviation of 1. This is pretty much it, guys. I hope you enjoyed it, and now you are able to run Monte Carlo simulations and know about risk management and how you can approach risk problems on your own. See you next.